Hello everyone, I am Poulami, and before I begin, I would like to thank the organizers for inviting me to give this talk. So, my talk is based on investigating a Lorentzian wormhole family, where I will primarily focus on the quasi-normal modes and echoes which are associated with this family. So, my talk is based on two of our recent works which are mentioned below. So, this is the brief outline of the talk. So first I will begin with defining what are quasi-normal modes and why are they really important in the present era of gravitational wave analysis. Then we will move on to discuss the geometric properties of the two-parameter Lorentzian wormhole family that we are basically interested in. And then we will see the corresponding energy momentum tensor and the properties of the matter fields associated with the spacetime. Then we will go on to study the stability of this geometry under scalar and axial perturbation. And finally, we will make a brief remark about the possibility of this wormhole family being a black hole mimic. So let us begin. So first, we would like to know what are quasi-normal modes. So whenever there is any dissipative system that vibrates, there is always a decay of energy associated with it. This loss of energy happens through complex, discrete, characteristic modes of the system, which, when imposed with proper outgoing boundary conditions, are called quasi-normal modes. In most scenarios, the wave propagation in spacetimes can be reduced to a second-order partial differential equation of a form like this, where this r star is the tortoise coordinate and V of r star is the effective potential which is associated with the spacetime geometry as well as the perturbation. Now, we can use separation answers like this to separate the spatial and temporal part. So the spatial part can be reduced to a very simple ordinary second order differential equation in terms of r star. And we can impose proper outgoing boundary conditions to get discrete values of this omega, which will not be nothing but the quasi-normal modes. And from the temporal part, it is well evident that omega has to be complex so that the real part will give us the oscillation frequency, whereas the imaginary part, when associated with a negative sign, will lead to damping of the signal over time. So this is important because this negative sign containing imaginary part will lead to proving the stability of the geometry over time. Now, for typical asymptotically flat spacetimes, the boundary conditions which are purely outgoing at spatial infinities will have a structure like this. So now we will go on to discuss why these modes are important. So when a gravitational wave observation is made, the modes are extracted from the signal. They verify the stability of the spacetime by, as I mentioned earlier, the decay of the signal over time. Next, these modes depend functionally only on the parameters of the source, and they provide useful insights on the underlying theory of gravitation through the metric that is used. And finally, they essentially dominate the late time ring down behavior of the gravitational wave signal. So now we come to the interesting part where we discuss the wormhole family that we are interested in. So this is the metric of the wormhole family. So this was first discussed in this 1994 paper by Shan et al. So just a minute. So this is the metric that was discussed in this 1994 paper by Shan et al. And this wormhole geometry, this B of R is basically the shape function of the wormhole. And the radial coordinate R is related with the tortoise coordinate L in a relation like this. So the two parameters that control the geometry are N and B naught. So this N is assumed to take only even values that controls the geometry of the spacetime. And this B naught is nothing but the throat radius. So you can see in the embedding diagram that is shown below that the blue curve is for n equal to 2 and the black and red curves are for different n values. So by choosing simply different n values, we can produce different wormhole geometries from the same wormhole metric that is mentioned above. This n equal to 2 case is a very well-known and well-studied geometry, which is called the Ellis-Pronikov wormhole. So now we will take a look at the matter and energy conditions that are satisfied by this geometry. So the components of the energy momentum tensor can be written as a sum of contribution coming from a phantom scalar field and some additional matter term that corresponds to only n greater than 2 geometries. So, and it is also observed that it satisfies the averaged null energy condition. So interestingly, this additional matter term leads to the flaring out for n greater than 2 geometries happening a bit away from the throat. So we get a long necked structure for the n greater than 2 geometries. You can contrast this with the n equal to 2 or the Ellis-Pronikov case, where the flaring out happens just from the throat. So in the n equal to 2 case, this additional matter term is not present, and hence the flaring out happens just from the throat. So in essence, we can call these n greater than 2 geometries as long-necked wormholes. So now we move on to the stability analysis of this geometry. So the scalar perturbation will begin by solving the box phi equal to 0 equation or the Klein-Gordon equation. And from this, the effective potential that we obtained has a structure like this, where the m is nothing but the angular momentum number. Now, if we plot this effective potential as a function of L, then we can see that for all n greater than 2 geometries, the potential is a distinct double barrier potential. So note that only n equal to 2, that is the Ellis-Pronikov case, has a single barrier. Rest all have double barrier potential. And the plot that is shown at the lower end of the slide shows a decay signal over time, indicating that all these geometries are stable. Now, the plot on the right basically shows the distinct sets of quasi-normal modes which are present corresponding to different geometries. Hence, we get distinct quasi-normal modes which are scalar of origin and correspond to different n values. So since it is a double barrier potential, obviously the signal will get reflected, and these multiple reflections will produce a repetitive signal which are known as gravitational wave echoes, which can be seen distinctly in this time domain profile. So if we take, say, some arbitrarily large value of n equal to 2600, then the potential peaks are very sharp and narrow, producing these distinct echo profiles in the signal. So what we observe is that there are double barrier potential for n greater than 2 geometries. The geometries have been observed to be stable. There are echoes observed, and the quasi-normal modes are distinct for each n geometry. Next, we move on to the axial gravitational perturbation, where we perturb the background spacetime itself by introducing a small tensorial perturbation term h mu. Now we will consider all equations up to linear order of this perturbation term, and we will be interested only in the axial or the odd parity modes. So in this case, the effective potential has a form like this. So if we again plot this potential in terms of L, we get a single barrier for n equal to 2 and 4. So you can contrast this with the scalar case, where we had a single barrier potential only for the n equal to 2 case. But here we get single barrier both for n equal to 2 and 4. Next, if we plot this effective potential for n greater than 4 geometries, say 6, 8, or 10, there we see that the effective potential, interestingly, turns out to be a triple barrier for lower n values. And if we increase the angular momentum number m, then these peaks basically merge to produce a single barrier. So it is indeed very intriguing that a very simple wormhole geometry like ours can produce and support such intricate triple barrier potentials. So we can correspondingly calculate the quasi-normal modes associated with this axial perturbation. So the decaying signal over time again indicates that all these geometries are very stable under this perturbation, and the corresponding quasi-normal modes are shown in the two plots on the right. So the x-axis basically shows the different n values or the different geometries, and each geometry has a distinct set of quasi-normal modes. So what we observe under axial perturbation is that all these geometries are stable, and the QNMs are calculated, which are shown in these plots, through numerical routines, the direct integration and Brownian extraction. And these distinct QNM sets have been observed for the different geometries, and echoes are not observed in this case because they are suppressed. Even though it is a triple barrier potential, these echoes get suppressed in the full time domain profile. And so we can't see them directly in the full time domain profile. So now once we have established the stability of these geometries, we now come to the question of this wormhole geometries being a possible black hole mimicker. So obviously, as the name suggests, these are compact horizonless objects that mimic certain observational. Yeah.
Maybe you can finish within 1 or 2 minutes.
Yeah. I'm on the last slide. Yeah, this is the last slide. So these are compact horizonless objects that mimic certain observational features of a black hole. So as Professor Cardoso had explained earlier, that these examples, some of the examples include wormholes, gravastars, boson stars, so on. So we now probe the question whether our wormhole family can exactly mimic the ring down features of the Schwarzschild classical black hole. So as you can see in the plots, the red curve denotes the ring down of the Schwarzschild black hole for m equal to 3 mode. And the corresponding green and blue lines indicate the ring down for the corresponding wormhole geometries n equal to 2, 4, and 6. So it is indeed interesting to see that the mimicking nature is obvious for different throat radius values corresponding to different n geometries. And the quasi-normal modes, that is the fundamental or the most dominant mode, is exactly found to be very close to the Schwarzschild black hole case. So the damping part or the imaginary part is very close to the Schwarzschild black hole, whereas the real part starts deviating from the Schwarzschild black hole case. So in essence, we can conclude that the real frequency reveals the identity of the wormholes, and the small n mimickers are better mimickers, small n wormhole geometries are better mimickers than the large n geometries. So this is where we conclude that we have done a detailed analysis of the 2-parameter ultrastatic Lorentzian wormhole family, where we have seen that the n greater than 2 wormholes are supported by a phantom scalar field and some additional ANC satisfying matter, which leads to the long-necked nature of this wormhole geometries. We have proven the stability of these geometries under scale and axial perturbations and have observed the quasi-normal modes and echo profile. Finally, we have seen the wormhole family as a black hole mimicker candidate, which has been explored at the end. So now I will stop here. Thank you.